And I've known Hugh pretty much, it's like 10 years at least now. So when I started in UL as a postdoc back in 2009, Hugh was there doing a PhD. And then when I went to Cork, after I did a postdoc in Switzerland, Hugh was in UCC as well in Cork. And then when I came to Limerick, Hugh also turned up in Limerick. So now as a lecturer. So we've had kind of parallel careers in totally different topics for the last 10 years. So it's a real pleasure to introduce Hugh here today. A very hot topic really on batteries. So I think it'll be a real pleasure. So off you go, Hugh. Looking forward to it.
Okay, thanks, Michal. So you can see the screen okay?
Yeah, perfect.
Yeah, so I said it actually in one of the tweets that the idea with the title was kind of the couple of purposes there. So it's for people who know batteries, essentially to annoy them, because the topic of super batteries is kind of controversial, and for people who don't know batteries, to entice them in the first place. So that'll become a bit clearer what I mean as I continue along. So just an outline in terms of what I'm actually going to talk about today. So the fact that it's a bit of a longer seminar means that I can spend a bit of time in terms of the battery technology landscape. So this is kind of my own perspective on it. Why it's important, obviously, I think it's reasonably self-explanatory at this stage, but I'll run through a couple of bits on this. So starting just with an EV as an example application for energy storage in general. Then we look quickly at some of the different chemistries that could be used for EVs and more generally in batteries. Focus then in terms of performance and sustainability of the different battery chemistries that I'll have spoken about. And then move into kind of the nitty-gritty of it. So looking at the gap between theoretical and practical performance on the different battery systems. The next topic then would be in terms of battery hype pitfalls. So again, this is such a hot topic and a big area that there are a lot of pitfalls that we can have in terms of hype, and we need to be very, very cognizant of those. And then my own research approach. So how I would say, at least in my own mind, how my own research is slightly different to some of the research that's ongoing in the battery area. And to show that, then I'll run through a couple of different examples from my own research. So I'll look at the scalability of emerging materials. This topic then is called half cell testing, half the story. So that'll be clearer once I go through it. And then depending on how much time I spend on the intro, I can also talk about some lithium-air battery research. And then just some outlook and conclusions at the end. So as I said at the start, we'll look at an electric vehicle as an example application. So again, this is our Tesla EV here. So what we have is some performance metrics and figures of merit here for this vehicle. So the battery cost at the cell level is about $115 per kilowatt hour. The battery cost itself is nearly $6,000, which is obviously non-trivial. The battery size is about 50 kilowatt hours and the range is about 380 kilometers. In terms of charging, then you can attain a 208 kilometer range after about a 30-minute charge. And then on a slow charging setup, we're talking more like 50 kilometers per hour. So you can see if we're at a 380 here, that we're over a 7-hour charge. So obviously that would be your overnight charging. So in terms of the battery chemistry that we're looking at here, for the majority of current applications, so you can think EVs, you can think stationary storage, and particularly portables, we're currently talking about lithium-ion technologies. So we have two main classes, obviously, of the electrode materials. We have the anode and the cathode. Anodes primarily are graphite. In this case, there's almost a secret sauce where it might be slightly boosted with silicon. So there might be a low portion of silicon in the anode as well that boosts the capacity. If we're talking about just the graphite on its own, the capacity of graphite is about 372 milliamp hours per gram, which essentially is just a measure of how much lithium can be stored in the anode. And then the voltage window that usually operates over is about 0.01 volts to 1 volt versus lithium. On the cathode side of things, we have the NCA in this case. So cathodes are slightly broader in that they'll tend to be a lithiated metal oxide material. So this is a nickel cobalt aluminium oxide. And you can see then that the stoichiometry of it is 0.8 in terms of nickel. So it's quite a nickel rich composition. In terms of capacity then, the capacity is about 200 milliamp hours per gram. Which you see is below the capacity of the anode, which means that it's the limiting electrode in terms of the overall battery, and also the voltage is very important here. So the voltage for NCA is about 3.7 volts as your average discharge voltage. Okay, so this is our Tesla that makes use of that technology. But for comparison then, a Ford Focus, which is roughly the same size as a car, will travel for 675 miles on a full tank of petrol. It's going to take only minutes to fully refuel, and it's going to cost about half the initial price. Now, find there is a slight markup for this being a Tesla, and it's nice and shiny and new, so that can explain some of it. But the battery cost is not an insignificant proportion of that cost as well. So essentially, what we want is to go on cheaper, longer range, faster charging EVs, and to achieve that, then improved batteries are going to be a major part of the solution. So in terms of some of the different chemistries that we could look at, so we have state of the art is lithium-ion, as I said. So strengths, it's an established system, it's proven, it has good cycle life overall. A lot of these obviously are relative, so it has good cycle life as a kind of baseline. You could have other chemistries that could have higher or lower than this. So it's always a good reference point that most of these will be compared to lithium-ion. And what it has in general is it's a good balance between power and energy for this lithium-ion. And again, that would be very cathode dependent. In terms of the weaknesses then would be in terms of sustainability that I'll talk about in the next slide. And there's obviously safety concerns as well for lithium-ion, particularly as we go to high charge. So if we class the next group of potential new chemistries as sustainable chemistry, so we're looking at things like sodium and aluminium, where the actual metal that we're looking at is more sustainable and usually cheaper as well. So some of the strengths of sodium would be it's sustainable, and also it's similar in a lot of its performance and its fundamental characteristics to lithium. So this could kind of expedite the development. We'd have made a lot of learnings from lithium-ion that could then be extended onto sodium-ion. But fundamentally, it seems that the energy density is always going to be lower in sodium-ion than it is in lithium-ion. On the aluminium-ion side, so this is probably slightly further behind in terms of development. Sustainability is even more of a bonus here compared to lithium and sodium. And also there's potential for the +3 ion that could allow for higher capacity of the material in the first case. At the minute, it's kind of hung up in terms of the electrolyte. So the electrolyte stability is a big issue. And also the electrolyte choices are drastically reduced compared to lithium and sodium. And as a result, linked to that, the actual mechanism for the battery is more complex as well. If we then move on to what we class high-risk systems, so these are probably further out again, although there has been some very good progress made in terms of lithium-sulfur batteries. So lithium-sulfur here, we can potentially get a higher energy density, and we also have the benefit of the sustainability of sulfur as a cathode material. One of the issues, though, is you have the requirement for a lithium metal anode. And we also, in general, have a shorter cycle life compared to lithium-ion batteries. And we have quite a complex mechanism in terms of how it operates. So we have major mechanistic challenges that we need to overcome. In terms of another high risk would be lithium metal, or also anode free. So lithium metal would be where you have a lithium metal anode and you have a conventional cathode material. So this obviously gives you high energy density. In terms of the anode free, you actually don't have any lithium at the anode side, and the only lithium that you cycle is from the cathode. So these have kind of seen lots of development in the last maybe year or 18 months. One of the main issues with this is the limited cycle life. So it's very difficult to work with the lithium metal anode, and I'll show a couple of the reasons why in a future slide. And we also have safety concerns as well. And lithium air battery or other metal air, they're systems that I will touch on briefly at the end, depending on how much time I've left, with some work that I've done before. So they have a very high potential energy density. Now we see that the gap between theoretical and practical sometimes is quite large, and we'll come up with a bit of an explanation for that. One of the major benefits of this is that you're using oxygen from the air as a sustainable cathode active material. But weaknesses again is there's very limited cycle life on this, and it's a particularly complex system in terms of the both the mechanism of what is actually occurring and also the factors that influence the performance as well. There's also other systems out there. There's things like potassium, calcium, and magnesium, but they're kind of in their infancy, and I won't really touch on them that much. So if we look in terms of the link between performance and sustainability, we need to look at the different areas that we have for the battery storage in the first place. So obviously everyone is now familiar with handheld devices. So we all have mobile phones. In 20 years, we've essentially gone from a Nokia 3210 that has a 1250 milliamp hour battery to about a 4000 milliamp hour battery in the latest Samsung phone there. So the battery is slightly heavier, but there is significant improvements in terms of the energy density and the capacity of that overall battery. And the battery cost then is about $30 for that phone. When we look at scaling up, then we go to an electric vehicle market. So if we take about 7,000 of those cells and put them together, we then get a Tesla battery module. So the cost of that module then is $7,000. And then when we take 1,000 of those modules and put them together, we end up in the ballpark of the stationary storage. So the motivation for this obviously is we need to store energy that's made from intermittent sources like wind and solar. So this is actually, I think it's still the largest lithium-ion battery in the world. So it's in Australia. It's probably more of a proof of concept than anything else, but it can, for a short time, power about 30,000 homes. And what you see as well is that the cost of this system is about $50 million. So it's not an insignificant cost in terms of actually building this. So one of the main issues in terms of particularly the lithium side of things is sustainability. So this is where all these new chemistries are coming in. So what you'll see, there's some key critical elements that are needed for lithium-ion that are very poorly distributed around the world. So particularly cobalt, which we'll see is in NCA, and in lithium cobalt oxide as well, is almost exclusively in the Democratic Republic of Congo. Lithium then is pretty much between China, Australia, and Argentina. So essentially all of the manufacturing of those elements are very localized, and as a result it means that places, for example, like Europe, are very poor in terms of battery manufacturing because we don't have the resources available to us. So what we could envisage as we move forward is a more kind of diverse battery storage landscape. So if we look at the differences with these three different markets, the handheld, EV and stationary storage, we have different key performance metrics. So on the handheld device, what could be important are things like the charging rate, the energy density, so that it can go for a long time during the day, and obviously the cost. So we want it as low cost as possible. On the electric vehicle market, we want high energy density and power density, which again usually work against each other. So you can have a battery that's either high energy or high power. So we need to find the sweet spot for performance there. And the charging rate obviously is a major hurdle for the electric vehicles. As we saw at the start, even if it takes a half an hour to charge, when you compare that to a standard vehicle, you're of the order of seconds. So it's a real issue for people having to wait for their EV to charge. And obviously calendar life. So you don't want to have to trade in your EV after 5 or 6 years. You want this to go for at least ideally 10 years plus. The stationary storage then is slightly different. The key performance metrics are cost per kilowatt hour. So the physical size of the battery doesn't necessarily make that much of a difference. Whether this massive battery here in the bottom right is this size or 1.2 times this size doesn't make a huge amount of difference. So the main thing is the cost, the safety, obviously, because you have a huge amount of energy stored in there, and the sustainability, and obviously cycle life as well. So you don't want to put this installation in and then have to rip it out in 10 years time. In terms of the current battery chemistry, so the handheld devices, we're looking at lithium-ion, EV is lithium-ion, and the stationary storage is lithium-ion. They have slightly different cathodes depending on the markets. So what we would suggest is that as we move forward in time, we're probably going to see a diversification of this energy storage. So as we go to future times, we're going to have sodium-ion or aluminium-ion could potentially come into handheld devices if the performance can be brought up to that level. The EV market, it's very difficult to beat lithium in terms of energy density, so it will likely be an advanced lithium-ion or lithium metal type situation. And then in terms of stationary storage, it would probably be flow batteries or sodium or aluminium-ion. So in terms of the gap then between theoretical and practical energy density, so this is a really nice paper that looked at the modeling of a system size for a given specific energy. So what we would have seen, and I didn't give the numbers, is things like the lithium-air system. You'll very often read a paper where it could be the theoretical energy density is comparable to gasoline. It's actually shown here. So it could be 4 times higher than the current state of the art. But when people actually start to calculate out the system that you would really need, you'll see that the improvements are actually far more modest. So in terms of the lithium-air system, it does win out on a watt-hours per kilogram, so that's a specific energy perspective. But in terms of a watt-hours per litre, which is the volumetric energy density, which is actually usually very important for things like electric vehicles, where you're limited in terms of the space that you can have the battery, the more advanced lithium-ion and lithium metal options actually come through. So if we were looking then at kind of the overall situation, you could compare the different battery chemistries in terms of certain key performance metrics and potentially where they might land. So if we look at energy density, our ideal battery chemistry obviously would be 10 out of 10. Aluminium-ion is probably never going to be as high. Sodium will be slightly higher. Lithium-air will be very high. Lithium-sulfur will be slightly lower. Same with lithium metal. Future lithium ions, this would be kind of taking lithium ion as far as it possibly can, would be slightly lower than that again. But we can then start to kind of come up with a full picture of which of the key performance metrics make sense for the various applications. So that's energy density. If we have cost, so this is the larger it is, the higher the cost. So as we go to lithium metal, it'll still probably be quite expensive because we need to make lithium metal, whereas the sodium ion and aluminium ion would be cheaper. In terms of sustainability, like I said before, aluminium and sodium hopefully will be more sustainable and will be more suited then to the larger scale applications. And then finally, then this is cycle life. So again, the ideal battery chemistry will be 10 out of 10. The lithium-ion, future lithium-ion is likely to have a very long cycle life, whereas the higher energy density ones like lithium-sulfur and lithium-air will likely have a lower cycle life. But that's not necessarily an issue. If you can get, for example, 1,000 cycles at a very high energy density, you can actually get away with some of this. So again, just to highlight and kind of give a snapshot for overall the development that is going on. The different battery chemistry groups, they have different strengths and weaknesses, and obviously there's variation within them. So within the lithium ion as well, the cathode choice plays such an important role that it can completely determine the key performance metrics there. So some of the general battery hurdles, and I get into some of my own research then quickly. So even in the established lithium-ion systems, there's lots of issues going on. So that these are really complex systems. We kind of forget, because we use these batteries every single day, we just take them for granted, but there are multiple issues that can become actual issues in terms of the performance that we need to be cognizant of. So on the anode side, we can have issues with the current collector itself. The binder can decompose. On the active material here, this is graphite. This is probably the most stable or one of the most stable anode materials that we can have. But even then, there can be issues with the graphite. So you can have particle cracking. You can have what's called SEI formation. So I'll show an example of that in a second, where it's unstable, it breaks down and precipitates like here. What you can have as well is this is lithium dendrite formation. So these are metallic lithium that deposits on the anode and essentially breaks through the separator and shorts the cell. And that's one of the main causes then of our short circuits and potential thermal runaways then. On the cathode side, so again, as we move to higher energy cathodes, they're in general more reactive. So what we can have is we have structural disordering. This is particularly true when we have high degrees of delithiation of the cathode material. We can get things like transition metal dissolution. So essentially you can leach out some of the transition metals from the cathode material that can cross over to the anode and cause all sorts of problems there. And you can have issues on the aluminium current collector as well. So I mean, this is within the established lithium-ion setup. So you can only imagine as we go to new systems, we're introducing new potential issues that we need to be aware of. So some of the more important ones with our research then are in terms of the solid electrolyte interface. So essentially what this is it's a mix of organic and inorganic components that form on the anode, primarily where we're interested, but also on the cathode. You sometimes see it called the CEI, the cathode electrolyte interface. And what it is it's a mix of these different components that forms on the surface through reactions of the electrolyte with the material. And what this can do is it can completely determine the performance of the battery. I'll show a couple of examples of the importance of this as we move on. In terms of general battery hurdles, as a kind of a general comment, there's definitely an over-reliance on what's called half-cell testing. So on the left-hand side, we've a half cell here, which is our active material. So in this case, it was germanium nanowires that we use, and it's tested versus a lithium counter electrode. So what people will tend to do if they make a new material for a battery system is they will just then test it in a half cell versus lithium or sodium or potassium. And essentially what it does is it doesn't properly mimic what's going on in a full cell. So again, this is our full cell, this is our lithiated metal oxide, and this is our active material here. So what we can do is we could do a huge amount of development of an active material, and if we've only ever tested them within half cells, we could completely neglect really important issues that are going to crop up as we go to develop these further on. And the final one then will be in terms of material expansion and structural changes. So again, as we move to higher capacity materials, so as we move to any of the other mechanisms beyond intercalation, so things like alloying or conversion materials, you'll start to come up with these issues and we need to mitigate them. So we'll have pulverization of the material, potential delamination. And also you can imagine this is usually a very thin layer, the SEI on the surface. And if you have lots of volume expansion and contraction, you're constantly changing the surface of the material, and this SEI can break and have to reform. And one of the key issues with the SEI, particularly for the alloying materials, is it consumes lithium. So if you're working within a full cell, you can actually deplete your lithium inventory for your entire battery. So you can have enhanced capacity fade compared to a half cell. Okay, so just before I go into it, so the battery height pitfalls, so I've been dying to do this slide for quite some time. So I've anonymized any of the text that I'm about to show, just to not offend anyone. But so this one I really quickly. Science has done it again. Another battery breakthrough is here to change batteries forever, this time by extending life thanks to nanowires. The battery advancement means that batteries can offer longer lives than current lithium-ion batteries. In fact, these nanowire batteries can withstand hundreds of thousands of charges without showing any signs of degradation. This could mean future batteries last a lot longer, ideal for electric cars. The result is no loss of power even when recharged 200,000 times over 3 months. Now we simply need nanowires to be manufactured en masse while advancing capacity. So essentially what this was, is it was a supercapacitor paper where they cycled a nanowire-based electrode 200,000 times over 3 months, and a journalist got a hold of it and completely lost the run themselves and thought that they had revolutionized battery technology. Another one that you'll see quite a lot of the time, again, Professor Joe Bloggs, leader of the research team, the quote is accurate while the name isn't. This could be a game changer, a paradigm shift in how a battery operates. So I'll be honest, if there was one phrase that I could expunge from humanity, it would probably be paradigm shift at this stage. And then the final one is, while smartphones, smart homes, and even smart wearables are growing ever more advanced, they're still limited by power. They say that the battery hasn't advanced in decades, but we're on the verge of a power revolution. Big technology and car companies are all too aware of the limitations of lithium-ion batteries. While chips and operating systems are becoming more efficient to save power, we're still only looking at a day or two of use on a smartphone before having to recharge. So the important context of that last one is that the battery cell energy density has almost tripled since 2010. So to say that the battery hasn't advanced in decades is frankly nonsense. So the difference here is going between paradigm shifts, as they're called, and incremental performance increases. It's not necessarily that the latter is not necessarily a bad thing. So we've seen significant improvements within lithium-ion batteries just by understanding the materials and also improving them. So what I would say in terms of take-home messages for this would be beware of the super battery. So again, that goes back to my title. So what will happen is researchers will often oversell their findings or be misrepresented by a journalist in need of a soundbite. So it's much more attractive if someone can say that they've completely revolutionized the way we think of batteries, rather than actually making what could be a very important incremental improvement. And obviously incremental improvements are not such a bad thing when it comes to battery research as well. So in terms of the research application, so what I would say is the common approach is people will make a new material. They'll make electrodes using standard methods. So they'll just use slurry processing to make the material. Then they'll test it using standard protocols to basically try and maximize those headline numbers. So try and get the highest specific capacity, try and get the highest energy density. publish the papers with those performance metrics that they've just gotten as their main selling point, and then essentially forget about the material and start all over again. So what happens then is we end up with these, on the TRL scale, we'll end up with these TRL1 materials that are just constantly being churned out and forgotten about. And in reality, the focus is solely on delivering these performance metrics, and the insight that we're actually getting is limited, and the ultimate impact, at least in my mind, is very questionable. So what I'm trying to do, at least on the research approach, is to identify open questions and issues in battery topics. So again, they can be over the different chemistries. Then with those open questions and issues in mind, use either materials from the back catalogue that I have made before or are available within the larger group within UL, or commercial materials if they're more suitable. And then if there's none of those materials that are suitable, go and develop new materials at that case, but again, with the initial open question in mind. Then to do relevant electrochemical testing to address those questions, but with focus on more atypical protocols. So not just simple battery cycling examples all the way, and looking at different conditions that, again, go back to our initial question or issue. And then the important part then is to perform ex situ characterization of materials, focusing on changes then in the active material. So how are these materials related issues linked back to our performance, and also focus on the SEI. So what this does, it allows us to have nice feedback loops into the testing. So we can find from the ex situ, if we need extra tests, if interesting phenomena arise from the ex situ and the performance metrics, or if we need to go all the way back again and look at materials tweaks from this ex situ analysis. So ultimately, the goal from this would be to deliver mechanistic insight, meaningful performance metrics. So again, they're tuned back to what the initial application is, with the goal of contributing then to the field and saving time as well. This can be quite a time-consuming process in terms of you can actually lead people down dead ends in terms of research, and then maybe finally move a bit towards our improved batteries. Okay, so finally onto the research now. So I just wanted to give a good bit of context on that. So in terms of the background of this, so this is for the lithium-ion research that I'll be talking about. So I would say anyone who has worked in battery research at all will have seen this image on the left-hand side. So this is a silicon anode. Silicon is a very high capacity anode material because it can essentially take on a lot of lithium per unit of silicon there. But what happens as a result of that is we get a large amount of volumetric expansion. If we use planar silicon, it will expand and contract and essentially pulverize. The same for films, you'll have a pulverization and a coarsening of the material. Nanowires then on the opposite side are a more attractive geometry, because what can happen is you can have expansion radially and also along the length of the wires, and essentially you can accommodate that volumetric expansion without pulverizing the material and destroying it. In terms of the directly grown materials here that we should see here, it's also attractive because you have a good contact with the current collector, so you can remove auxiliary components like the binder and conductive additive, potentially reduce the weight and increase the energy density. So in terms of the materials in UL, so this kind of started in terms of the synthesis side during my PhD, where I worked with another colleague, Chris Barrett, and we developed a system where we could grow germanium nanowires in a glassware-based approach. And then from there, it was taken over on the battery side by Ty Kennedy, who really kind of pioneered this research. So there's a couple of really nice findings from the outset with this. Was germanium is a very high capacity material that was well known beforehand, but in terms of the stability of that capacity, it's absolutely outstanding. So what we found is he found after 1,000 cycles, the capacity was almost 1,000 milliamp hours per gram, which is nearly 3 times that of graphite. In terms then as well of the mechanistic side of things, so what he found was that these pristine nanowires over the lithiation and delithiation cycles, they completely convert into this porous network of active material, which is very, very stable then over long-term cycling. So again, as Michal said, when I came back to UL, I was tasked with basically trying to scale up these materials for an Enterprise Ireland project. So what I found with the initial substrates that we had previously used, stainless steel, for growth, was that as we increased the mass loading on this stainless steel, that the performance started to suffer essentially. So this is a very common issue within I wouldn't say within the literature, but it's a well-known issue that is actually not shown in the literature very often. So this is one of these kind of hidden hurdles that people may not necessarily address and really deserves attention. So some of the motivation here was that we need, for a practical anode, we're going to need a capacity of over 3 milliamp hour per centimeter squared. So the question at the start was, how does this performance scale as we increase the active loading? So what I wanted to do was systematically vary the mass loading and investigate the performance. Okay, so you can see the loading of the different anodes as we continue along here, up to 1 milligram per centimeter squared. So again, obviously, it's quite obvious that as we increased the loading on these anodes, that the gravimetric capacity started to decrease, essentially. So whereas we had the very light samples, the performance was absolutely rock solid. As we increased the loading, it started to decrease. In terms of the aerial capacity here, so this is the same data just plotted with an aerial capacity, you'll see that they all started to bunch together towards the bottom there. So we couldn't, with this setup, achieve a capacity over 0.5 milliamp hours per centimeter squared after 250 cycles. So what the first point was to actually see, could we understand this? So on the lowest loading, the 0.2 milligram loading, we found that we had these nice isolated active regions of the material. And then as we zoomed in, we had the lovely porous network that Tig had previously seen. So again, that was all consistent with what we had seen before. But as we started to increase the loading, we started to come up with new materials-based issues. So as we had to 0.4, we had larger active regions. So you can see these are at the same magnifications, but the active regions are larger. And what we started to see was this deviation from the ideal material porosity. So we started to see almost chunks of active material that had come off and become inactive or had stopped cycling. As we went to 0.6, we started to find these larger regions where the material had fused together. And we also had evidence of uncycled nanowires here. And then as we went to the higher loadings again, you could see that we had a disintegration and delamination as well. So the material was no longer properly connected to the current collector and had broken away. And in terms of the micron level active material then, so we couldn't see any obvious porosity in the active material. So this led us on then to the use of a different current collector to see, could we get around those issues. I mean, a lot of the issues as we went to the higher loadings previously, you see, were due to disconnection with the current collector. So we looked at textured copper as a current collector and grew the wires directly on it. One of the benefits of this was that we could grow the wires directly on the current collector without having to do an initial evaporation of a catalyst material. So we had previously established that you can grow nanowires directly from copper foil. What happens essentially is you form these copper germanide seeds in situ on the substrate, and then the nanowires will grow from those. So what we were able to do was get very nice loadings of the germanium nanowires grown directly on the copper current collector here. So when we compared these copper-based current collector nanowires to the ones that were grown on stainless steel, we had a dramatic improvement in terms of the capacity retention. And you can see that this is from starting out at the same aerial capacity here. So at the end of 250 cycles, the capacity retention was about 2.7 times better on the current collector than it was on the stainless steel. One of the main issues, or one main reasons explaining this, was that we physically couldn't remove the nanowires from the current collector prior to the testing within the battery. So if we took our germanium on stainless steel and sonicated the nanowires, they would come off, whereas on the copper, they were deeply embedded in the current collector and very well attached and wouldn't come off. So obviously what we needed to do was explain this enhancement. So again, back to the end of the story almost, in terms of looking at the materials and how we can then explain what we've seen. So in this case, on the left-hand side, this is our textured copper anode. And what you've seen is that the material is now properly adhered. We have these large areas of the active material, but also there's porous material formed as well. So you maybe can't see it from this SEM image here, but we did TEM and it had the same kind of characteristic porous network that we would expect for germanium. Whereas in the 1 milligram stainless steel anode, we had complete delamination. Essentially, as soon as we took apart the cell, the material flaked off and there was very little of it actually left. So we had no network formation and pulverization of the material. So you can see that there's a clear explanation at the materials level why the performance is enhanced here. So the next question then became, can we push this loading even further? So I had quoted 3 milliamp hours per centimeter squared as a potential target. So I'll show that in 1 second. But one issue that people don't necessarily do is they don't test their materials to failure. So what we found here is when we continued on beyond the 250 cycles, that we had this abrupt failure mechanism that seemed to occur just before 300 milliamp or 300 cycles. So when we looked at this with the EIS, then what we found is we had a major impedance increase after at the failure point. So what we found is if we actually disassembled the cell here and then reassembled it with a fresh lithium counter electrode, that the performance jumped back up here again once we did it at a C/20 restart. So this was done without an SEI removal as well. So this is just due down to the way that the impedance occurred on the electrode. So essentially what had happened was that the processes that we were looking to do in terms of the lithiation had moved out of our potential window that we were investigating. In terms of increasing the loading even further, so we could bring it up nearly to commercial levels in terms of the aerial capacity. So we could bring it to nearly 3 milliamp hour per centimeter squared. But what we did find was that the capacity dropped off more rapidly than beforehand. So what I wanted to find out was, once we had reached this point here where you would think that the battery had failed, essentially, was to disassemble the battery and look at the active material. So what we found was that we had perfect retention of the material on the substrate, and we also had the porous germanium network formation. So essentially this issue here was not directly linked to the germanium. So what we did was we removed the SEI from there and reassembled the cell within a new fresh half cell and started the cycling again, and this capacity jumped way back up again. So in this case, the issue was actually due to the lithium counter electrode. So essentially what we had was we had a failure of the lithium counter electrode, and once we had reassembled the cell there, our capacity drastically improved. Okay, so in terms of future work, so there's still open questions with this, but we have gained a lot of mechanistic understanding in terms of what has gone on and where we can go in future. So the future work would be full cell testing of these high loading anodes. So as I mentioned before, full cell testing is kind of neglected and is something that needs to be done a lot more. And also then we need to see, can we remove those lithium related counter electrode issues. So in terms of full cells, when we're looking at the full cells, what's really important is the background importance in terms of anode and cathode balancing. So if you look at the specific capacity of cathode materials, you see they're usually no higher than 300 milliamp hours per gram. But as we move to things like silicon and germanium, they're much, much higher. So they tend to be multiples of the cathode material. So what you can imagine is if you have a pristine germanium nanowire, you lithiate it, you will obviously expand it, but you'll form an SEI as well. So this PN ratio, or it's also called NP ratio, needs to be as close to 1 as possible. So essentially, if you have to introduce any excess capacity, you will do so by adding more cathode material, but there's a disproportionate penalty in terms of the weight to the cell to do that. So what you will do is if you have to have excess lithium in there to accommodate any losses of lithium due to SEI, you'll have to bring in more cathode material, and you could completely dilute any of the energy density benefits of having a high capacity material in the first place on the anode. So there's a couple of ways of doing this. So there's nice contact methods where you can pre-lithiate the material to try and get around those irreversibility issues. And there's also electrochemical methods like the one I'm going to show on the next slide. So in terms of a half cell, again, we have a large excess lithium due to the fact that we have a lithium counter electrode. And then what happens as a result of that is that lithium losses in the SEI can be mitigated due to that excess lithium. Whereas in a full cell, we've little, if any, excess lithium in the cathode. The SEI has to be accounted for with extra cathode material or with an anode pre-lithiation. So if we have continuous SEI formation, then we're going to lose cyclable lithium, and it's going to lead to capacity fade. So in terms of contrast in half cells and full cells, so these are our results then from the paper. So these are our half cell cathode cycling, and this is our half cell anode cycling, and this is our voltage profile then for our full cell charge and discharge. So this is for a germanium and LCO full cell. What we found is the voltage window is very important in this case. So this is for a full cell that had quite a large cathode excess. So there was more capacity on the cathode side than could be accommodated on the anode side. And what happened essentially is just above 3.9 volts, if you continue to charge the battery, you'll have this secondary plateau here, which we found is due to lithium plating. So what can happen is you can have a secondary process beyond your standard lithiation where you have lithium plating. And as I've highlighted, that's a major issue in terms of full cell operation. So again, I'm conscious of the time, so I can go back and discuss the intricate details of this if people like. It's just to kind of get across the main points of these. So what I did then was looked at the cycling comparison of the different setups. So what's very important is the electrolyte composition here. So if we look at as a function the PN ratio here, so this is the essentially how much cathode excess we had. So the blue trends here have more cathode excess, and as we go down to the red, they have less. So the best in terms of performance was the one that had VC in terms with the electrolyte and within what we call the standard voltage limits. So to avoid any of this lithium plating issue, we set our upper cutoff voltage at 3.9 volts within the full cell and cycle the battery between 3.9 and 2.8 volts. And so what you'll see is in this cell here in B on the right hand side, the cycling performance is essentially comparable with a half cell germanium. But as you decrease the excess of capacity from the cathode, you start to see a diminishing capacity over time. So essentially what has happened is we have diminished some of that active lithium within the cell, and we started to lose capacity there. So again, there were some extra tests just to kind of really hone in on the mechanisms that were going on. So if we did a full cell charge, what you could see, this was for a PN 1.5. This is full cell testing where I disassembled the anode afterwards and then put it back into a half cell. So this is with a fresh lithium metal, and what you'll see immediately is that the capacity returns to what you would expect it to be, and also the capacity retention is enhanced. So basically, this is the summary of the difference between a full cell and a half cell. You far greater depletion of the capacity over time in a full cell. But on the other hand, when a PN3, so we have a very large capacity excess on the cathode side, and this capacity drop off is far less pronounced when we have a PN3. So finally, what we did was some conditioning of the anode and cathode, or the anode side. And what we found was that the number of electrochemical lithiation cycles that we did drastically improved the performance. So when we went from a full cell that had no conditioning, after 100 cycles, we could only deliver 301 milliamp hours per gram based on the anode material. Whereas when we went to 50 cycles, so essentially we lithiated the material for 50 cycles and delithiated for 50, took it apart and put it into a full cell, that we could still retain 437 milliamp hours per gram. Now, what it is worth noting is that is still well below the theoretical capacity or what we would expect for germanium. So obviously this is something that needs to be drastically improved in terms of the long-term cycling. So one silver lining that has come out of the work in terms of the full cell performance is that the rate performance, so how this battery behaves at high rate. So say 2C here means that the battery will charge in half an hour and discharge in half an hour. 5C again would be a fifth of an hour, and 10C then would be 6 minutes. So you can see that in each case here, the full cell performance is actually drastically higher than the half cell performance, particularly as we go to 10C here. So in this case, the full cell is actually giving us a capacity that's nearly twice, or it's more like 3 times higher than the equivalent half cell. So at high rates, the full cell consistently outperformed the half cell. So the implication of this is that if you're only looking at half cells as an indicator of how your performance is for high rate materials, that you're actually drastically underestimating the performance at those high rates. So the future angles on this work then would be to look at kind of dynamic potential windows. So if we have increased polarization during cycling where our processes are moving out of our voltage windows, we may need to increase the upper cutoff while also avoiding lithium plating. And the big one then is improved pre-lithiation procedures. Also looking at better anode cathode pairings. So again, there is scope for potentially increasing this high rate performance by looking at a cathode material that is particularly good at high rates, and also different operating conditions. So work is already underway where we're looking at these full cells at both high and low temperature in terms of trying to improve the performance. So I wonder actually, Michal, how am I for time? I'm conscious
You've all the time in the world.
Okay.
Yeah.
Okay, I'll try and keep it to 10 minutes.
If you can stop maybe at 5 to or a bit after, but there's no panic.
Okay. So I was conscious that I may have a lot of time or very little time at this stage. So I'll just briefly touch on 2 lithium-air studies that I had done more to whet people's appetite, and you can, if you're really interested, you can read the paper on the backing of it. So the battery chemistry of lithium-air is completely different to lithium-ion, and it's well worth a look. It's from a fundamental perspective, it's really, really interesting. So what we have is, ideally, all we want is solid lithium peroxide formed and then broken down on the discharge and charge. But as a result, we now have a solid product within our battery. So the shape, size, and crystallinity of that lithium peroxide is going to completely influence how the battery charges as we break that down. So in general, with lithium-air, we have large capacities possible, but it's a very complex reaction chemistry. Even if we just have the sole lithium peroxide formation and decomposition, it's quite complex. So there's lots of issues with it. We have cathode instability, we have electrolyte instability, anode instability, and actually even diagnosing what the performance is due to. So you can have almost phantom reactions where you have side reactions that completely take over your cell. So again, to briefly touch on the different parameters, you can look at the oxygen supply in terms of dictating the performance. So we have the pressure and purity, with water content, which is really key, with the cathode composition, with the electrolyte composition, the separator that's used. Again, you can imagine that's going to influence the gas permeability and the stability and water content of that. The anode stability, so we're talking about a lithium metal anode. If you have oxygen crossover, you can start to get reactions at the lithium side, and also the water reactivity as well. Obviously, the operating temperature, the current collector, and the cell type and architecture. So the point here is that any change to the above parameters is going to completely change how the battery performs. So what has happened to date is we have had a lot of these standalone scattergun studies where people will just try and get the biggest capacity numbers that they can get to maximize their impact. But then there is all of these open kind of mechanistic questions still out there. Now, there has been lots of progress and lots of really nice understanding developed around the mechanistic side. The 2 very brief papers that I'll talk about was work that I had done in UCC. So in terms of the current collector choice, so it really does matter. So we have types that are used. So we have a stainless steel mesh, nickel foam, or gas diffusion there. So it's a carbon-based electrode. So what I found when I was analysing the data on this was that, suspiciously, at least in my mind, was that the highest capacity numbers seem to always be for carbon-based and nickel foam-based electrodes, whereas the stainless steel-based current collectors were usually much lower. So the testing that we did, this is probably the most rudimentary testing that we ever had to do in terms of delivering a paper. But what we did was we did discharge tests on the various current collectors with focus on the gas diffusion layer in particular. So this is a carbon-based system. And what we found out was that, obviously enough, there was lithium peroxide was forming on the current collector. So when people were going back and calculating capacities for active materials that they had placed solely on the current collector while neglecting the mass of the current collector, they were drastically over reporting their values. So these are kind of characteristics. They're called toroids. Very often they're donut shaped, and that tends to be the way that the lithium peroxide forms on current collectors. So I won't dwell on this too much. If people are interested in the results, I can ask it during the question section. But what we found clearly was that lithium peroxide was forming just on the bare GDL, as it's called, and inflating the capacity numbers. Another interesting study then that we did is manganese oxide is widely used as a catalyst material in lithium-air batteries as well. So what I wanted to do was investigate how it impacts the discharge and recharge chemistry. So we had a number of different electrodes and also electrolytes. and looked at manganese oxide nanorods that we formed very straightforward in a solution process. And what we found was these products started to form after the discharge. These were very large lithium hydroxide side products that had formed on the manganese oxide cathode. So as I said before, these were actually giving us capacity during the electrochemical cycling, but it wasn't reversible. So it was killing our long-term stability, but was giving us capacity in the first place. But what we found really interesting was that it was actually specific to the surface as well. So within a mixed cathode where we had a super P, which is just carbon, and a manganese oxide region, that we had preferential formation of these lithium hydroxide deposits on the manganese oxide regions, whereas on the super P regions, we were only forming these spherical or toroidal lithium peroxide deposits. Okay, so apologies for rushing the last couple of slides, but I can come back to and talk to them if needs be. So just a couple of conclusions. So again, I really dwelled on the opening half an hour intentionally. So the kind of conclusions to take home would be that battery improvements are generally incremental, and that's fine. You know, if for the most part, if we have this axis here, this is crudely drawn by me. So if this is your hype cycle, these are the ones that are paradigm shifts, and what tends to happen is they fizzle out because they've never been taken to the higher TRL. Whereas if we look at incremental improvements, you can drastically improve it. Now, that's not to say that new systems can't come in every so often. I mean, the lithium ion system at one stage was a paradigm shift, but to just be cognizant of any of these batteries that are kind of panaceas that solve every issue that's out there, these super batteries usually come with lots and lots of caveats. As we move forward, then there's lots of different battery markets. So we have, handheld, EV, all the way up to stationary storage. So what's likely going to happen is we'll have suitable battery chemistries for each, where the performance characteristics of our battery chemistry is matched to the application. So these new chemistries then are going to take time, but they're likely to make an impact in those emerging markets. And then finally would be beware of the numbers and hype. So you really need to try and get a insight into what's actually going on. So to my mind, at least, the mechanistic insight is all important in terms of this area, and is the only way that we really stimulate improvements in batteries. Okay. Thanks for that.
Thanks a million, Hugh. Brilliant, really accessible talk. Perfect for the audience, actually. So maybe if we can stop sharing the screen. And if anybody has any questions, they can write in the chat, or they can just ask directly.
Hello.
Hi.
I have just a small question.
Sure.
Because I noticed your experiment is set to a square centimeter, right? The cell.
Sure.
Yeah. So have you tested a large cell, more than a square centimeter?
For which materials?
For example, your anode condition of half cell and the full cell cyclic up to 200 cycles. Your paper in, I think, 2019.
Okay, we haven't, but it's a really important thing as well. One point that I didn't make is that the scalability in terms of the testing is very important. Even in terms of the anode and cathode geometry is very important.
Okay. And another is a general question, because I'm not familiar with because recently you see we all the country develops the battery, so the car. So we not trust. We sometimes we have the limit for forbidden for the traditional car use the oil, use the petrol, but I'm still concerned about if do you think this tendency is correct, or because we are more focused on the developers, how to say our effort is switch to the the new energy car, but but the new energy can have actually also have the problem from the pollution about, for example, the battery. The age of the battery is a bigger factor, because sometimes yes, we can switch the battery and just change the box, but for this battery, the life cycle is maybe the 250, but after that, we don't have the solution to solve this kind of, because for the life of a car, for the traditional, it's more than, you see, 20 years. Maybe, yeah, but
I think I definitely get your question in terms of the idea that an electric vehicle isn't by definition going to be cleaner than a standard car. I mean, if you have materials that aren't sustainable in there, if you use a huge amount of energy in extracting the materials in the first place, which is the case at the minute, and also the recycling is a major issue. So the cheaper the materials, the less of an incentive there is to recycle them. And also there isn't the volume of materials to recycle at the minute. So it's only one part of it to make cars that run cleaner during the lifetime of it. But if you have something at the end of it, you need to be able to reclaim the materials and make sure that it's green. So, I mean, for example, we are on some European projects where we're looking at the life cycle, the entire life cycle. And that's one point that really is important.
Okay. Yeah.
Thanks, Gufan.
Yeah, thank you.
Thank you.
Thanks.
There's a couple of questions coming in, so I'll just read one first. It's from Craig Armstrong. So, could you elaborate on the method for synthesizing germanium nanowires? And could you please explain how the glassware setup shown in the diagram and photo is used towards the beginning of your experimental section?
Yeah. So again, that might have been one of the areas that I rushed through a small bit. So I'll just go back without sharing the slide, and I can just talk through it. So. What we use, it's a solution-based approach. So it's the glassware is very straightforward. It's heated within a three-zone furnace. We've standard lab glass, and then high boiling point solvent that is squalane, and then we inject a precursor into that. So we've done a couple of variations for the ones, for example, that I did in the copper current collector. That was actually done within a glove box, so it can be done on just a heated a hot plate, obviously, and you can drop cast the precursor directly onto the current collector. So we have a couple of different variations as well. We can do silicon within the same system too. So the important point is you need some sort of catalyst material that's going to induce the one directional growth. So we tend to use either copper or tin that induces that nanowire growth. But in terms of the processing temperature, they're all below 500 degrees Celsius. We use kind of the standard liquid precursors, so it's diphenylgermane or phenylsilane on the silicon side. And I'm trying to think that the reaction times then are usually below an hour. So it's quite straightforward, and it's in terms of the scalability, then we are looking at different avenues where we can make it scalable. That's one of the, I guess, hurdles for any lab scale synthesis. So I hope that addresses that, Craig.
Yeah, no, definitely. So
elaborate.
I know Craig, so if you want to come to Limerick and have a look in real life, Craig, that's no problem. And email me and Hugh if you want more details. And I think you published that a couple hundred times at this stage. how that's set up. So yeah. I'll keep going. So Kat,
hi.
Hello.
Hiya. How are you?
Question. Sorry, I'm Craig's supervisor. Good question, Craig. We're obsessed with the setups and glassware and how people are doing it because they don't reveal it in their work. So we're like obsessed with that. I just had a question about that impedance buildup. I thought it was really interesting that it had that 300 cycle cutoff point.
Yeah.
Was that every time? Was that no matter how much materials you made, how many times you made that setup? Did it always cut off at around 300 cycles? And then when you restarted it, was it again until 300 cycles, or was there some kind of memory effect in the material?
So what I would say that 300 cycle is dependent on the loading. So it occurred faster for higher loading materials. In terms of the memory effect, I'm not sure, did we did we restart it, continue along the cycle? Again, it would take, you know, a couple of months to get to that point again. But something I would be interested in seeing actually is if when that reestablishes it again. My guess would be that it would probably occur faster. In terms of if I remember the data correctly, so when I restarted it and say the capacity jumped back up again to where it had been before, that was at a C/20 rate. So there was an element that was, you know, if we're saying about the impedance, it almost brings the process back into the voltage window by just virtue of having it at a lower applied current density.
So was that original cycle not at C/20?
No, they were done at C/2.
And then you reinstated it at C/20. Okay.
Exactly. Yeah.
Okay. That's interesting.
And even in terms of the voltage profiles, it was very apparent. I mean, from say the differential capacity plots, you see the peaks very clearly for the alloying and de-alloying reactions. So when we went to the C/20, they were right back in.
Right. Okay. I'd be interested to know what the memory effects are on these materials, because you see a lot of these papers coming out now where they're like, oh look, we can just restart it and it resumes it if we just do this little treatment. But there's going to be, I mean, entropy happens, right? You can't stop these processes taking place and then leaving their mark, and then that's going to short the future performance of that material. So you can sort of temporarily reinstate that, but how long does it go on for?
Yeah, and I mean, I in no way am I thinking that it's fixed. You know, essentially, I would be interested in seeing how that changes if we did it again. Kind of extend that study a bit.
Cool. That was a really fantastic talk. Thank you for taking the time on that 30 minutes at the start as well, especially. Really, really interesting. I like the overview. I like the
thanks, because I honestly never get a chance to do any talk like that. So yeah.
It's feeling. No, thank you for that. Really cool.
Thanks.
Okay, I'll keep going. So Mohammed raised his hand there a while ago. If you have a question.
Hello there.
Yeah, we can hear you.
Hi, Asif. Yeah. We can hear you.
You show in a PPT in a slide.
No, we can't hear you anymore, Mohammed.
We can't hear you.
Lower than the full cell. So what could be the reason? Mostly for full cell capacity, I believe lower than the half cell.
Okay, so there's a couple of reasons I would suggest. So I think an issue of it is depletion of the lithium inventory in the battery. So that would lead you to lower capacity. There's also an element of the voltage window within the full cell. So because we had done a fixed upper cutoff of 3.9 volts, and we know that we have impedance build up as well, that will shift over time. So if you look at the voltage profiles, they will raise over time in terms of the full cell. So you're not getting complete lithiation of your anode material on every cycle then. Mm-hmm. So it's not one issue, it's a combination of multiple issues. So that's why I had said in terms of the voltage windows that we probably need to look at kind of dynamic voltage windows that change over time to compensate for that impedance increase while not having lithium plating.
Okay, thank you so much for the answer.
Thanks, Steve.
Thanks, Mohammed. Andy, you raised your hand as well.
Hi.
Hi, Andy.
So I have two questions. One is, you mentioned germanium, and then you sort of talked about lithium and how it's accessible around the world. Is germanium more accessible, or is it also got similar issues with, you know, it's going to be found in certain
question. Yeah, I don't know. Is the honest answer. Germanium, to my mind, germanium is expensive, and it's not going to be as all of these materials. It's not going to be a panacea. It's not going to be in EVs. It could find, particularly on the performance side of things and the performance characteristics, it could be in niche applications. It's much better at high rate than silicon is, for example. So if you need a high capacity anode material for a small high power application, then germanium could be your material. Yeah.
And the other part is, should we be, so riffing on the question from earlier, is should we be designing the batteries to be recyclable, given these materials are so expensive? Or is it just too difficult to get the performance up to consider?
No, they should be. And that's the idea. I mean, with modular designs, that's the way they're trying to make them so that they're recyclable by design. But that's one of the things with battery development in general is it's so multidisciplinary.
Sure.
I mean, that's an engineering issue, really.
Right.
But I mean, where you can and the other thing is, if you do reclaim the material, you have to have it in a process that is energy efficient as well. So I mean, if you to do 1,000 degrees treatment to get your material back in the first place, it's not sustainable.
It's not good.
Yeah.
Okay. Thanks,
Andy.
Thanks, Andy. I'll read out another chat question here from Samad. Interesting talk, Hugh. So there's a lot of hype in the media regarding supercapacitors. They have the potential to hold huge amounts of charge and are capable of supplying current at high rates. Are under development. Do you think supercapacitors can replace batteries in the future?
It's a good question. I would think, from what I've seen of supercapacitors, that the energy density is the problem in terms of direct replacement of batteries. But again, it's the application-specific angle. So there are applications where supercapacitors are better suited, without doubt. So we need, put the supercapacitors where they belong and stop saying that supercapacitors are going to solve everything. It's picking out the applications that make sense for the different chemistries and energy storage devices.
Yeah,
but good question.
Yeah, definitely. Okay, I have one question, Hugh. I think we might have talked about this at one stage, but like this is an electrochemistry seminar series, and you're definitely I think that lithium-ion batteries is dominated by materials scientists. Mm-hmm. That the electrochemists are slowly diffusing towards it, and so, where will the electrochemists have the biggest impact on the lithium-ion battery basic research? What help do you need?
But personally, for me, I mean, what interests me is the mechanistic side of things. Is understanding. I mean, the very good question on the impedance is someone who is an expert in impedance coming in and telling me, rather than us just using it as a diagnostic tool where we have an issue, someone takes that on and says, oh, well, I'm going to see if there is a memory effect. I'm going to, really pushing on beyond my understanding of the particularly, say, AC impedance, because obviously they're a whole other skill and discipline beyond the real material side of things. But I do
taking a step back kind of and going to more traditional materials and build up a new kind of set of standard experiments, maybe to go deeper in the mechanism.
I think that's worthwhile. I mean, this is one of my points, is that it doesn't always have to be the new wonder material that you're doing your test on. It can be commercial materials, and in some ways it's more impactful. I mean, if you're looking at LCO, which is a cathode material used in probably millions of devices, and you can give real insight in terms of the performance of that, that's hugely beneficial. Whereas if you've come up with a niche cathode material that's never going to see the light of day because it has some fundamental flaw that you haven't identified when it's scaled up, then any amount of really good analysis isn't going to be that useful.
Yeah, I agree. I just think you're showing towards the end there, maybe you showed me the graph before, that they were quoting numbers beyond the theoretical limits.
Yeah.
And it was just because the mechanism wasn't understood, basically.
Yeah.
And okay. Great. If there's no more questions, we can wrap it up for Hugh.
Yeah, hello.
Yeah. I don't know who's speaking.
This is Ibrahim. Can you hear me?
Yeah. Hi, Ibrahim. How are you?
Yeah, good. So Hugh, I just wanted to ask a question on the key materials for batteries. So on the map there you showed, we see almost cathode, anode. Europe seems to lack these materials. So do you know what plan is in place for these materials, or you are looking at different chemistries, or you just depend on the open market to acquire these materials?
Do you mean me personally, or your
No, not you, as in the general research in Europe?
In general, I mean, there's huge efforts on the European side in terms of lobbying groups and kind of things like the Battery 2030 Plus, where they're looking at raw material sourcing. There's huge amounts of push from Europe to establish battery manufacturing. I'm trying to think in terms of the kind of unofficial positions on different chemistries. I mean, China and the Far East are so far ahead on lithium-ion batteries that is going to be very difficult for Europe to fully catch up. There's definitely scope in sodium for Europe, but then they have to have, like I said, they need to have their application that they're targeting. So say if Europe are saying, right, we're going after sodium for stationary storage, then that's the way to commit to it. But to my mind, the lead for non-European countries on the lithium mining is going to be very difficult to catch up on.
Okay.
Okay. Yeah. Any other questions, Ibrahim?
Yeah, it's fine. I'm okay. Just
great. Okay, so thanks everyone. And thank you. A lot of questions there. A lot of kind of science and predicting the future. So in terms of how and where the battery is going to be made. So thanks you. Before we finish, I'd just like to introduce next week's speaker. So it's Gregor Herzog. So Greg will give a couple of seconds about what he's going to talk about next week.
Yeah, so next week I'll be talking about mesoporous silica and how to prepare mesoporous silica modified electrodes, and how we can characterize them and use their dimension and their chemistry to use them in electrochemical sensors.
Great, yeah. Look forward to Greg. See you next week. So thanks again. So Hugh, you are the host now, so you can cut us all off.
Okay, great. Sorry.
We'll see you next week.
Thanks very much.
Thanks, you.
Thanks everyone for listening. Bye.
Thank you.
Bye.